Okay, we can see you now. So whenever you're ready.
Wonderful. So I am a senior forest restoration scientist at the Nature Conservancy, which is one of the world's largest environmental NGOs. Though, of course, I speak with my own opinions and do not attempt to reflect the opinions of a diverse and large organization like the Nature Conservancy. And I focus on methods to restore tree cover. You may notice I switched the title from Reforestation, and I did that for a reason. So I've been at the Nature Conservancy for over 5 years now, and I was hired right when this paper came out. This was led by Bronson Griscom, and it was an attempt to quantify all the different ways we could use nature to help tackle climate change. And reforestation was the largest bar, had the greatest biophysical potential. But if you're looking closely at this bar, you notice there's a little star at the top of the error bar. And that's because there's huge uncertainty around the potential to use reforestation as a climate solution. In fact, the confidence range is 50% greater than the actual estimate itself. It's a range of 15 petagrams, where the average value is 10 petagrams. So that's my job, is to try to improve our understanding of all the different ways we can restore tree cover to offer climate mitigation and try to reduce the uncertainty around those estimates. And usually I say it boils down to two things: the rate, how much carbon you can get per hectare of investment, as well as how large and where are the areas of opportunity to restore tree cover. I'm just going to talk about rates today, but I worked on both of these elements. And at the Nature Conservancy, I often get questions like this. I just got one 2 days ago, where the standard email is sort of, Susan, if I do this type of project in this location, sort of how much carbon can I get? You know, ballpark estimate by the end of the day is great. And these are people who are writing grant proposals or trying to do sort of an early policy assessment, trying to figure out what options would be possible and viable. And so, you know, they don't need a perfect number, but they need something pretty good. And I will admit that I hate these emails because I'm a scientist and I want to give people good numbers, and just sort of like ballpark estimate by the end of the day is not what I want to do. And so for the last 5 years, I've been trying to prepare myself for these questions by pulling together all the information that's out there so that I can rapidly respond to questions like this when they come in. The problem is that the default carbon sequestration rates that are out there are usually too coarse. So these global ecological zones are what the IPCC uses to provide default estimates to plug into calculations. And while this analysis is a little old now, from 2015, there they found that the majority of tropical countries are using these, they're relying on these default estimates. But it's usually a single rate for an ecological zone. So that large purple blob in the middle of Africa would get a single rate estimate. And we know that there's a lot of variation on the ground as far as how much potential carbon accumulation would happen if you were to invest in a project in that location. The good news is there's lots of information out there. The bad news is that it's too distributed to be useful. So what I do is try to pull together all of that information into a usable form for people to tap into to make these quick assessments of opportunity. And it's somewhat similar to the great plot networks that we discussed yesterday, except not highly controlled. It's just sort of taking what's out there and trying to pull it all together. So back in 2017, we started a very large literature review, trying to find all the carbon data we could find for lots of different approaches for restoring tree cover. It started with 11,000 abstracts. We read about 5,000 of the papers fully, and in the end found over 1,000 that had some estimate, field-derived estimate of biomass and or carbon, a geolocation, and some described some method for restoring tree cover. So I keep saying the words restoring tree cover rather than reforestation, because I have sort of a larger umbrella definition of what we might do. And there's lots of ways. So you could intend to bring back a natural forest, and you could do that through natural forest regrowth, just sort of stopping what's ever disturbing it, putting up a fence, taking off the cows, letting the trees grow back on their own. You could go in and do some sort of spot planting or large scale planting to try to restore the native forest. but also you could set up an agroforestry system where you're integrating trees amongst crops or livestock. And then, of course, there's methods to set up systems that are intended to provide timber, like monoculture or mixed species plantations. And depending on the approach, it's going to have different impacts on the cost of implementation, the benefits to people and nature, as well as the climate mitigation. So that's why we partition it across these different strategies. And in our original literature review, this was sort of the coverage by those different types. We first tackled natural forest regrowth because that is really just nature doing nature's thing. So it was easier to compare across the globe. And it serves as a good baseline to evaluate more intensive efforts or techniques for restoring tree cover, such as those that require active planting. And so to be included, a paper had to provide some sort of empirical measure of carbon, as I said. We prioritized those that gave a stand age between sort of 5 to 30 years because we're interested in what's possible in the near term to help tackle climate change. Geolocation, and if it was a soil measurement, it had to have a control so we could evaluate change in soil carbon stocks. And then, of course, there was a lot of work to extract the data and a lot of work to harmonize the data as best as we could. And in the end, we had over 13,000 measurements of carbon stocks that came from over 250 papers, plus we had 3 national inventories in there. And the literature-derived data, not the inventory data, is all now freely available on GitHub. So if you're looking for this data and you can't find it, let me know, but it's out there in sort of the raw form. But the people that we work with don't have time to sort of download the data from GitHub and analyze it for their own purposes. So we also pulled it together into a map where we combined the field data that we had accumulated with 66 environmental covariate layers to predict across forest and savanna biomes potential carbon accumulation from allowing natural forests to regrow the sort of first 30 years of stand development. And general patterns are not that surprising, right? Higher sequestration rates in the tropics compared to in temperate or boreal regions. But what we did find was that there was over 100-fold variation depending on where you are. So if you look at the scale, it goes from 0.06 up to 6 tons of carbon per hectare per year. And it can vary fairly substantially on small scales. So for example, one of those FAO ecozones that the IPCC used, we found 8-fold variation just within one of those sort of blobs. And this is 1 kilometer resolution and can be found on Global Forest Watch if you are looking for it. The good thing about this is we are able to improve this map over time. So we're currently redoing it to incorporate more training data. We now have over 230,000 training points, a large part and thanks to Tom and Adriani who pointed us to all of the inventory data that they spent years trying to aggregate. We are also running the clock out longer. So instead of stopping at 30 years, we're going out to 100 years, in part because we got requests from folks at the IPCC that were like, well, but what about the older forests? Do you have any information to help us there? And if we're running the clock out 100 years, we also want to account for future climate feedbacks because these are based on historical rate estimates that may not reflect future conditions. And then, of course, we can also better account for spatial autocorrelation with new techniques that came out that doesn't substantially change our results because our data were already well distributed. So that's natural forest regrowth. The larger chunk of literature actually covered monoculture plantations, which was tackled by Jacob Bukowski and Cyril Melikov, who are at UC Berkeley and now at Conservation International and the Environmental Defense Fund, respectively. And, you know, I work at an environmental NGO, so of course, am not super excited about people setting up monoculture plantations, but it's an important one to consider because when you look at what people intend to do, a large chunk of what countries are planning to do around forest restoration is to set up monoculture plantations. These are the estimates that we were able to compile, 4,000 plus estimates of above ground carbon stocks that came from over 400 studies. There's 2 studies that provided a particularly large chunk of data, so those are symbolized differently here. And I'll flag this should come out in a couple weeks, any day now. So this paper is hot off the press soon. And this is what we found, is that there's high variation in carbon accumulation rates depending on tree genera, the plant functional type. Here are these deciduous trees, coniferous, et cetera, as well as biomes. And they're also impacted by whether or not the species are native and how the land was used previously. So again, sort of drives home the idea that sort of single default estimates that people use all the time are not accurate enough, that there's a lot of variation out there that we can help to explain. Right now, what we're working on are various agroforestry practices. I don't know if that counts as forest for this crowd here, but the reason that I'm particularly excited about agroforestry is that it is a very common strategy. So this is a paper that I really like that Meredith Martin put together. She's now at North Carolina State University, where she and her team looked across 170 plus tropical tree planting organizations, basically every tropical tree planting organization that they could find that had publicly available information. And they went through all of that publicly available information to figure out what on earth are people actually doing, because we hear all of these debates about people are doing the wrong things, planting the wrong trees, but it's sort of in the absence of real information. We didn't actually know what people were doing. So what this paper found is that since the 1960s, there have been 1.4 billion trees reported planted, which is a large amount. Interestingly, only 18% of those organizations actually mention monitoring, and only 5% mention survival. So we don't know a lot about the fate of these trees. But if you look at the trees that people are planting, the top species are agroforestry or timber species, right? They're like cocoa, tea, moringa, mango, and coffee. And what that tells me is that what people want are these useful trees. And so if we are trying to bring reforestation, restoration of tree cover to scale as a viable strategy to tackle climate change, we've got to focus on the types of systems that people want. But again, the default rate estimates that people are using for agroforestry are too coarse. So what you're seeing on the left is a reanalysis of the data that was included in Remy Cardinal's 2018 paper, where he and his team produced new default estimates for the IPCC and explained their methods. And they partitioned rates by sort of type of agroforestry. But then when we acquired the data and showed the carbon density across all the data points we've gathered, you can see that the distributions are primarily overlapping. So it's the above ground biomass on top and changes in soil carbon stocks below. And in particular, silvopasture is one of my favorites, thought of over 100-fold variation in above ground carbon in silvopasture systems alone, because those can range from sort of one tree, few trees in a grazing patch to like sheep underneath a dense overstory. So, you know, saying like, I'm setting up a silvopasture system doesn't actually provide you much information of how much carbon might be stored within that system. So our goal, again, is these large data compilations. I spend all my time scraping carbon numbers from papers to answer how much climate mitigation potential can agroforestry offer? How does that vary by practice, by location, by management regime? Agroforestry is particularly complicated because there's all different ways you might manage those systems. As we always do, we produce a publicly available raw database that sort of reflects the data sort of as it comes from the paper. But again, most people that we're trying to help don't have the time or the inclination to scour all of the data that we pulled together. And so our plan is to put together some sort of tool to make it easy to acquire best estimates of predictors. This is the bar or the pie chart you see is from another meta-analysis. And they found that they were able to explain about half of the variation by thinking about the type of system, the prior land use, and the age of the system, but then there was a whole half of it they couldn't explain. So we are also collecting a whole bunch of covariates to see if we could do a better job of explaining variation. So right now we've gone over 18,000 papers. We've got about 1,000 that look good and over 10,000 data points already pulled that are estimates of carbon stocks along with their covariates to predict agroforestry mitigation potential. Have decent coverage so far, predominantly in India, Indonesia, Brazil, and North America, but I'm proud that we've got some good coverage in Africa. And I was surprised at the coverage across practices. So a lot from shade-grown commodities, followed by intercropping, timber plantations, and then these other approaches. So I'm slightly over, but my last 3 points that I wanted to make was that there's a lot of information out there, but it's too distributed to be useful for decision makers and needs to be aggregated into these raw databases and easy to use tools. Our knowledge is growing, our world is changing, and we need these things to be dynamically updated by the scientific and practitioner community, right? Like somebody spending 3 years like we do pulling together carbon data just doesn't keep pace with the rate of knowledge generation and climate change. And the last thing is a plug for improved temporally and spatially precise biomass estimates. Usually what we get from the paper are quite vague. And I get people like Laura Duncanson calling me up and saying, oh, can we use our data to calibrate our remote sensing estimates? And I said, sure. And then we look at it and I was like, I'm sorry, we don't actually have the date of when that estimate was taken. So it doesn't work for your purposes. So with that, thank you very much for giving me a chance to share our work with you today.
Okay, thank you very much, Susan. So as usual, if you have questions, please hold on to them until the end of the session. And we're now moving on to the next talk by Mark Rounsevelt from the Karlush Institute of Technology in Germany.
Good morning, everyone. Thank you very much for the invitation to be here. Hopefully you can all see the slides clearly. Could somebody just give me a nod and I'll just continue. Great. Thanks. Well, my name's Mark Rounsevelt. I'm from the Karlsruhe Institute of Technology, as just mentioned. I'm also at the University of Edinburgh in the UK. And I'm going to be talking about, with a focus in Europe, although there are lots of messages that are really relevant here at the global scale. We need to look at reforestation issues globally, as I'll introduce to you in a moment. And I think actually my talk is going to be a nice follow-on from to increase the area of forest is to enhance the land carbon sink as part of climate change mitigation strategies. And this is just some data taken from a publication that you'll see here, which looked at, if you try to achieve the Bonn Challenge target, 350 million hectares of new trees planted globally, then depending on the type of ecosystem restoration that you're engaged in, you get very different quantities of carbon. So that pretty much just reinforces what Susan was just saying. But actually what I'm particularly interested in, and what I'm going to be talking about more here, is actually the area questions themselves. And the question we have to ask ourselves is, okay, if we think that the Bonn Challenge is a good idea from climate change mitigation purposes, from forest ecosystem restoration purposes, then where does this quantity of land, the 350 million hectares, come from? Yeah, and just to put that into context, the area of the European Union, 27 member states, is 420 million hectares, right? So you're nearly talking about an area of land about the size, almost the size of the European Union. So that's a significant amount of land. So let's just have some reflection on where we can find that land in order to encourage reforestation. And it ultimately comes back to being a fundamental question of the competition for land. So land is pretty much a finite resource. There's only so much of it. There's a lot of competition for that land across multiple sectors, the food and fiber production, obviously reforestation, energy production in terms of biomass, but also finding space for solar panels and wind turbines, but also for nature conservation across a wide range of different biomes and living space for people. So there's massive competition for this finite resource. And we know that there's a big policy initiatives going on at the moment as well. So again, within the European Union, the EU biodiversity strategy has a target of planting 3 billion trees by 2030. It sounds like an enormous quantity of trees, and I'll come back to that number a little bit later on. So where will the land come from for these types of targets? The EU biodiversity plan, the Bonn Challenge, etc. That importantly avoid something which is really critical in this debate, which is the displacement effect of reforestation, or otherwise termed indirect land use change. And this is some interesting data I've picked up here from Our World in Data. And what this shows, each point is an individual country, The y-axis shows the annual change in domestic forest area, so domestic reforestation in each of those countries. And it's been plotted against the deforestation that's embedded in the imports of goods to those individual countries. And the imports are primarily, in